In this class we're going to learn about the Moivre's theorem. It's a bit of a scary looking theorem when we finally get it on the board. It looks a little like the last couple of classes we've done, and even the word, it seems strange to the eye. But don't get too afraid of it. It's not that scary. It actually is going to be something we're going to be able to use without thinking too much about it. And it'll lead to some powerful tools. It will let us do things like, let me put something up here, 1 plus I. I'll pick a simple enough complex number because I don't want to have to do too much work at the end of this. But we'll be able to get the power of this really easily. Now this is what the Moivre's theorem helps us to do. Now we can already probably do this to the power of 2 without too much trouble. We'll write out 2 brackets and we'll be finished in a few seconds, really, 10, 20 seconds. 3, we might not be too worried again, maybe a minute or two. But what if I gave you something like, I've done one of these out now, let me just have a look, 14 I've picked. If I asked the student to do this by expanding out brackets, I'm not sure how long it would take. 1, I would imagine it's nearly guaranteed to make a mistake somewhere. But 2, I think it might take an hour or so. I really don't know. I might have to test it one day because I'm always threatening students that'll be a punishment. Using the Moivre's theorem though, the punishment's out the window because I'll be able to just get the answer here quite quickly. It'll take about a minute or so of work. I'll do it at the end of this video, but I will get an answer out of minus 128i. Now usually an answer, the number will be quite big because we're still getting the power of a pretty big number. That's why I picked a fairly small and simple number here. So if you get something this powerful, you often will get numbers that are hundreds of thousands. So that's first thing to be a bit worried about. Also, this one's quite symmetrical. So we ended up with just an I. There's no real part to this. So it's quite a neat looking expansion actually. But a more random number, like let's say 3 plus 2i, that would give us a much weirder answer if we got that to the power of 14. I don't know what it is, but I'm guessing, I'm just trying to do quickly in my head a little, it'll be something like 100,000, like let's say 100,000, a number that big, or bigger, I really have no idea, plus another number, let's say 200,000. Something like that, except it won't be nearly that neat. There'll be square roots, there'll be a mess all over the place. But with the same amount of work, I could do this question as well. I won't do this one because it's just too messy. The answer doesn't look pretty, really. But I'll do this one by the end of the class, using just this, the Moivre's theorem. So let me find the Moivre's theorem for you now. And to do that, I'll just like to remind of the last 2 classes. 2 classes ago, we showed how to change a complex number that looks like this, one that looks like these guys here, into one that looks like this. Now, I really cannot emphasize how important that is or how useful that is, or more to the point, how the same these are. You can write it this way or you can write it this way. They both have uses, and this one's really useful for adding together. This one is really useful for multiplying together, and that's what powers are. Powers are multiplying. And yeah, last video then we showed how to multiply them together. And 2 complex numbers, instead of multiplying by 2 brackets, it was something we could just write down the answer simply. The R's just multiply together. The thetas just add together. It was something we'd be finished in moments. And that's really powerful. Okay, so that will move us on to the Moivre's theorem. What if I multiply the same number by itself over and over? And let me take this one as the example maybe. 1 plus I. And put this equal, a little reminder how to do this one. I don't think there's any harm, okay? So let me draw 1 plus I. That's about here. That's 1 and that's I. So how do we turn it into this form? We just need the or. That's the length here, or. So this is just a triangle. It's 1 high and 1 wide. So by Pythagoras' theorem, 1 squared plus 1 squared is 2. Square root of 2 is or. Square root of 2. And then we just need the angle here. The angle we can get by the tan of the opposite over the adjacent. That's tan, the inverse tan of 1. But also this angle should be clear, that's just 45 degrees. Or how I like to use radians, so 45 is pi over 4 is this. So this is just cosine pi over 4 plus I sine pi over 4. So it's not too difficult to change things from this into this form, but when in this form it's so useful. It is. Let me just rub this out. This was just to help me work this one out. Okay, so now if I ever want to get to the power of something, just by this rule here, the power of 2 I'll do as an example really. The power of 2, the power of 2. All it means is this bracket multiplied by itself. So I have that up here, or 1 by or 2. Or 1 and or 2 are the same. So this multiplied by itself will just be square root of 2 multiplied by square root of 2 is just 2. This angle plus the angle it's multiplying, which is it's the same. So this angle added to itself. 45 degrees plus 45 degrees is 90 degrees. Or pi over 4 plus pi over 4 is 2 pi over 4. 2 pi over 4 is the same as pi over 2. So cosine pi over 2 plus I sine pi over 2. That's it. I've squared it. It was quite easy to do. Let me put it in a more general form though, well, as we're getting the Moivre's theorem. What if I had some sort of complex number? I won't start this way though. What if it looked like this? Or cosine theta plus I sine theta. Now again, I cannot stress enough, every complex number looks like this. 1 plus I looks like this. 0 minus 128i can look like this. Any complex number you think of can look like this. So what would happen if we square this? If we let's do it this way. Let's do to the power here. Let's put in a little line here. How about power of 1? Just looks like this. Power of 2, what would it look like? So we've just done it here really with numbers. It's or multiplied by or. Well, that's just or squared. And it's cosine theta plus theta. Well, that's just 2 thetas. Plus I sine 2 theta. What if we got to the power of 3? Well, here's the power of 2 already done for us. So we just need to multiply this by this. Or times or to the power of 2. Well, that's or to the power of 3. Cosine, the angles just add together. We learned this last video. 2 theta plus theta. Well, that is just 3 theta plus I sine 3 theta. You could do it again. I won't explain why, but it's just like I said, it'll just become or 4. And just like previously said, it will just become 4 theta. So hopefully you're seeing the pattern here. So what would it be if I continued any number I want? And we write that in maths by just writing n. Any number we want. That n could be 3. It's already done there. It could be 109. It could be 14. The answer will always just be or to the power of n. Whatever number you want, you just put it there. Cosine, whatever power you're going to, just goes there. Multiplies by the angle. Plus I sine n theta. This is actually the Moivre's theorem. This right here. This one right here is the Moivre's theorem, or maybe just to put it more accurately, if we start off with something, or cosine theta plus I sine theta, if that is to the power of n, it is equal this. This here is the Moivre's theorem. And it's extremely powerful, and don't worry, you don't have to remember it. It will be given to you in any exam. In the Irish system, it'll be given to you in your formula book. Other countries usually just give you a piece of paper, and the Cambridge International anyway in an exam. I'm not sure of all systems, but I'd be confident enough that they probably mostly give this to you. If not though, it should be fairly simple to remember and figure out if you follow these steps here. So that's how we could get the power of any single number. And remember, 2 videos ago we learned how to turn this into this. So every number looks like this. Every complex number does look like this. This number, we already did it here at the start. We turned that into one that looks like this. So we're actually ready to do this answer already. It's very quick to do. Any number that looks like this to the power of equals this. So let me rub out the answer. Hopefully we'll find it again. And this guy is equal to, if we put it into this form here, it's equal to square root 2 cosine pi over 4 plus I sine pi over 4. I realize this is probably getting a bit small for people. To the power of 14. That is the same as that. It's identical. And now that I have it looking like this, I can use one of the most powerful tools, the Moivre's theorem. This looks like this. Has an or, square root of 2. It has a theta, pi over 4. Has an n, 14. Let's just write out what the answer is then. The answer is square root of 2 to the power of 14. Looks scary, but we can do that in a calculator. Some of you will be able to do this in your head even. This is not too hard of a sum. Cosine 14 multiplied by pi. Well, let me just write it down like this. 14 pi over 4. Well, yeah, let's divide this in now. Let's divide 2 into both. That gets a 7 and a 2. Plus I sine 7 pi over 2. There we go. This is an okay answer. It's not perfect. I don't like it too much. Well, let me clean this bit up first. Square root of 2 is 2 to the power of a half. A half multiplied by 14 is 7. So it's really just 2 to the power of 7. Cosine 7 pi over 2 plus I sine 7 pi over 2. Ask yourself what's wrong with this 7 pi over 2. And to show you what's wrong, let me just make a little bit of space over here. Let's try and turn this number back into a one that looks like this. So remember what you have to do. Or is just the length of the line, and theta is the angle we go to. So try and go to this angle here, 7 pi over 2. 7 over 2 is 3.5. So you can think of it as 3.5 pi. Well, here's our angle. 1 pi is here. 2 pi is here. 3 pi is here. 3.5 pi is down here. So it does work. This is perfectly fine as an answer, but it's a bit pointless. We don't tend to use numbers over 2 pi. You can. Usually an exam will tell you not to. They'll tell you to leave this answer less than 2 pi. But so what I've just shown here is 3.5 pi is the same as 1 pi, 1.5 pi. So this answer, this 7 over 2 pi, we'll talk more about this when we do trigonometry. Next video we'll do a little more of it. I realise it's a little unfair to you guys that trigonometry is being used this much when we haven't done it. But hopefully by the time you're watching this video, there'll be a link in the bottom that shows you to my trigonometry section. Okay, so really the lesson here is 7 pi over 2 is the same as 3 pi over 2. It's 3.5 pi is the same as 1.5 pi. It's also the same as 5.5 pi. Just going around 2.5 times. 7.5 pi. We already have 7.5 pi. You'll be going around 3.5 times. 9.5 I mean. It's all the same answer. Actually, minus 0.5 pi is also the same answer. So that's an interesting thing about trigonometry and complex numbers, in fact, in that we can write it that way. 2 to the power 7, I promise a lot of you, some people can do it in your head. 2 to the power 3 is 8. 8 by 8 is 64. So that's 2 to the power 6. By another 2 is 128. But use a calculator if you're not sure. 128, and this is cosine. Like I said, instead of 7 over 2 pi, we can always just take 2 pi away. If I take 2 pi away, I get 3 over 2 pi. Remember, 2 pi is the same as 4 pi over 2. Might be going a bit quick for some people. Pause the video, go back, listen back, ask me questions in the comments. I'll help you out as much as I can. And 3 pi over 2. And yeah, let me do that over here then. What is this equal to? In 2 videos ago, I hopefully have gone back and changed it by now, but I don't think I have time for a few months anyway. In the video where I changed it from this to this and this back, I never pointed out how easy it is to change back. You don't have to draw a picture. I still like this for some reason, but it's much easier. This can all just go in a calculator. 128 multiplied by cosine 3 pi over 2 will give you an answer. This cosine of 3 pi over 2 is 0. Well, I have room to write here. And this is just equal to 0. 128 multiplied by I sine 3 pi over 2. This is just minus 1. This bit here. 128 multiplied by minus 1 is minus 128. And there's an I here. That's the answer I promised you. You don't need to write 0. Minus 128i. One last thing here. Well, actually, yeah, one more thing. I might do one more thing after this. Just one interesting thing about this number. 1 plus I. It started off here. And if we multiply by itself, we would have got... we would have got a number here. This guy is 1 long. This is actually square root of 2 long. If we multiply by itself again, we get, I believe, over here somewhere. And this would be, I'm failing on my maths a little bit, but I think this is square root of 8. I'm not guaranteeing all these from this point. If we go down here, if we multiply, so this is to the power 1, to the power of 2, to the power of 3, to the power of 4 would become, this would just be 4 long, I guess. And so this is like number here is minus 4. And if we multiply to the power of 5, down here, oh, my maths again is struggling. Square root of 32. 32. And one down here would be square root of 64, which is just 8. So this would be down minus 8i. And so on. It's this interesting pattern. You can see it'll go around like this. And if I zoom out, because we've actually done it 14 times here, we've gone around 1.5 times. If you were to zoom out on this picture, it would look like this. And if I stayed going, this would actually probably expand a little faster than that. This number 14 here is, that's why it does have some importance, this 7 over 2 pi, this 3.5, because we're going around once 2 pi, 3 pi, sorry, 2 pi here, 3 pi, 3.5 pi. There's the answer we got. If I had gone to the power of, I don't know, 28 or something, we would have been somewhere around here, I think. I'm not really sure. I'd have to multiply out. It's quite interesting. Hopefully that sparks somebody's interest. And I'd love you to ask me questions about that. Last thing I wanted to do, I don't have room for it. I just wanted to point out that if they gave you the complex number in this form already, and they were happy to keep there's no reason we need to use this ever. Something we show you at the start. If they gave you the complex number in this form to start your question and asked you for this form at the end of your question, we would have been done in seconds. It would have been going from this line to this line. We just would have to write out the answer really quickly. Maybe we'd have to check how many times around the circle it went, but that wouldn't have been too much trouble. Okay, so that's the Moivre's theorem. Again, any questions, put them in the comments below. It's a bit complicated, but it's really easy to use. And once you figure it out, it's quite beautiful. In fact, complex numbers in general are quite beautiful once you figure them out. Okay, thank you for watching and have a good day.